This ninth question, I think I'm going to skip this because it doesn't look very practical to me. Why would I have to memorize this, whatever this thing is, right? Uh, yeah, pretty much just going to skip this. I don't think it's property worth proving. Moreover, it's just a lot of calculation. I don't like that. I mean, you can do it. You can try it out and see if it's correct or not. I won't. I don't see any way that I can just get this directly, and that's why I just won't. Okay, fine. So 10th question, let's do it. Normal inclined at 45 degree to the axis of this ellipse is drawn. It meets the x-axis and the y-axis in P and Q. If C is the center of the ellipse, show that the area of triangle CPQ is this thing. Oh, so normal is at slope 1, meets the axis and y-axis in P and Q, huh? Okay, fine. C is the center of the ellipse. Show that the area is given by this thing. Okay, I guess it's not that bad. Okay, it can be bad. So if it was a tangent, you would just use y equal to mx plus all that stuff, right? But now you don't have that accessory, so instead you have to go by the parametric form. So of course, just have x a upon cosine minus y b upon sine is equal to a squared b squared, right? Now what we want is the slope should be 1, right? So what does that mean? This means a sine upon b cosine, that is to be equal to 1, right? Basically a sine is equal to b cosine, or you can just say, okay, tan theta is equal to b upon a. Okay, cool. And what we really want is the area of triangle CPQ, right? So wherever it like intersects with those, fine. So whenever x is 0, your y just becomes a square minus b squared, and that times of s upon b magnitude wise, right? Not caring about the sign, the sign of the thing. Okay, and similarly, you just have a square minus b squared, and then you got c upon a. All right, and half of that's gonna give us the area. It's half of a squared minus b squared squared. Then you got sc upon AB. Now what is SC? That's hard actually. Okay, maybe I just divide by 4AB and then got a squared minus b squared squared. And then 2S is a sine of 2 theta, but that can be written as like 2t upon 1 plus t squared. So like 2 times of b upon a upon 1 plus b squared upon a squared, which is basically like 2ab. 2ab upon a squared plus b squared. Nice. Yeah, looks like that's correct. Okay. Yeah, that must be correct. Okay, then this cancels, just get 1 upon 2 right here, and then just get 1 upon 2. Hey, is that what we have to prove or not? Yeah, okay, that's it. Next question. So 10th done. 11th, tangents are drawn to the ellipse from a point. Okay, this point. Prove that they intercept on the ordinate through the nearer focus. Sorry, you got some random point. It's not random, but some point. You prove that the tangents intercept on the ordinate through the nearer focus. So at a distance equal to the major axis. So like this, huh? You got this as the tangent and this as the tangent. You just want to figure out, okay, wherever these will intersect, what's the distance basically, right? Yeah. Okay, but this is just a just some point which we don't even know. Does it actually sit on this? Doesn't look like that to me. Means would be like a square upon a square plus b square, and then you got this guy squared. Oh god, no. I don't think it sits on that, right? Yeah. At least doesn't look like that to me. Okay, we have to prove that the intercept on the ordinate through the near focus is a distance equal to the major axis, right? So this whole thing is equal to a. That's okay. Let's just figure it out. How would we try to do this thing? You can figure out the chord of contact. Yeah, that's not really helpful. You'll actually figure out. You will have to figure out the tangents themselves. That's not It's not worth doing, is it? No, it's not. Something else. Something else. I just want a distance between these, right? One thing, come on, think. What if I do like, okay, this plus, okay, that lies on a tangent, and this plus that, this also lies on a tangent. Sure. Okay, you got these two slopes, the multiplication of these slopes or something like that. That we know. Okay, that we know. Wait a second. Do we really care what these points actually? No. All we care about is the geometry. So like this distance, and then you got these two slopes. We know what these two slopes are. It's like this slope, the magnitude of that, times this thing, this distance, and then magnitude of this slope times this. Right. Add them up. That should be the thing. Now for this particular case. But actually, what you should do is this distance d, and then m1 minus m2. Just need to figure out what this is going to be. Okay, so D is not that hard because it's just dependent on the x coordinate, right? So let's just say this is x naught, y naught. So we really just want x naught minus AE, assuming it's actually farther, whatever. Okay, and then M1 minus M2, how do you get that? So y minus mx squared is equal to, in this case, instead of that, I'll just use y naught x naught. That's equal to a square m squared plus b squared, right? So we can figure out what m1 minus m2 should be from here. Right, so it's gonna be like a square minus x naught squared, and then you got m squared plus 2x naught y naught times m from here. Then you got plus b squared minus y naught squared is equal to 0, right? So this whole thing, the suppression of the roots, isn't that just, right? What is the suppression of the root? It's like negative square root of the discriminant, or yeah, that thing upon, okay, that thing upon a, I think. Well, whatever, we'll do it the other way. So right, and it will just be this guy. So negative b, yeah, negative b upon a squared, that's going to be m1 plus m2 m1 plus m2 squared, right? So negative 2x naught y naught upon a square minus x naught squared, all of that squared. Okay, and then minus 4m1 m2, which would just be 4 times of this thing, b square minus y naught square upon a square minus x naught squared, and then you want to take the square root of that, which is like 1 upon a square minus x naught squared. Just take that out. You got square root of, well, that's gonna come out anyway, right? Yeah, it's only 4x naught square y naught square, that's what we care about. Then you got minus 4, take that 4 outside as well, just make this 2, then all you really care about is minus a square minus x naught squared, and that times this thing, b square minus y naught squared, right? Yeah, sure. So this whole thing is like a square b square minus a square y naught squared, and then minus b square x naught squared, and then plus x naught square b y naught squared. So this cancels. It's going to be negative of this guy, which is like a square y naught squared plus b square x naught squared minus a square b squared, right? So on the square root of that, and that times of this guy. So 2, and then this thing upon a square minus x naught squared. Sure. And now you just have to plug this thing in and get the thing, right? Oh, that's horrible. Do I really want to do this? I don't feel like doing it. Okay, what choice do I even have? Let's just do it. 2 square root of, now wait, maybe like a square y naught. No, that won't happen. It just won't happen. You know that, right? So y naught square, this guy. A power 4 plus a square b square. Oh, this cancels. Perfect. Then you got b square times x naught square. So it's supposed to be all of this thing and that times of. Is that right? Yes, I think that's right. Yeah, sure. So let's do it. So this cancels, you get like 2 a power 4 right there. I mean, this whole thing. Yeah. So 1 is known as b square. That cancels from that, a power 4. And then you got b square x naught squared. You have to deal with that. So, okay, x naught squared, something like that. So b square a square upon a square as b square. All of that upon, yeah, upon a square and x naught squared. It's like take that a square common. It's supposed to be 1 minus 1 upon a square and b squared, right? Oh, it should be a power 4. It should be a squared in that case. Fine, fine, fine. So you got 2a square root of a square plus b square upon a square minus b squared. No, no, it should be upon a square. Okay, okay. Calm down. Let's do it the other way. So a power 6 and then, oh god, no. That's just way too much. Okay. What was the thing once again? It was b square x naught squared. So b squared times all of this thing squared, right? Oh, it should be a power 4, of course. That would make it correct. So 2a squared square root of 1 plus b square upon a square as b squared, and then you got upon a square and then 1 minus a square upon a square. Right, this will just turn out to be a square upon a square as b squared. And this thing will turn out to be minus b square upon a square and b square. But what we really want is just the magnitude, so don't worry about that. Yeah, that should be doing it. So then this we can, okay, we can just make it go up. It's going to be like 2a upon b square root of a square minus b square. Is that what the length should be? It's equal to the, what? Equal to the major axis. It doesn't look like that, certainly. No, it's not. It's not just, how can it be? It's not a. No, that's not right. Something went wrong. X square root over there. It's supposed to be x square root, right? Of course. Where did this other term go? It's not equal to the major axis. No. As you saw, it doesn't. That makes some kind of mistake. Probably I did. This whole exercise, I'm just starting to hate this because it's just a lot of, I mean, it has no nice properties. When would you actually use this thing? Nowhere, right? Right. And for what I did, doesn't look like it's equal to a, right? It just, yeah, it doesn't look like that. That distance must just be, what is this distance? Wait, did I forget to multiply? Oh yeah, I forgot to multiply by the d value. Ooh, but I still got this thing. Wait, what? How did that happen? Okay, let's multiply by d and let's see what we get. So d is supposed to be, you know, oh wait, oh, maybe that will work because this whole thing will come once again. Oh, write it in a different form. So this is going to be ae, of course, like 2a square e upon b, right? And then you got to multiply by x minus ae, which is this whole thing, which is actually just ae. No, a upon e, sorry. And that minus of ae, right? I guess that's how it's supposed to be. Yeah. Okay, just looking once again, it'll mess up anywhere. Slightly I did. I don't see anything though. It's supposed to be b squared. Oh, it's supposed to be b squared, not just b. Okay, I did mess up somewhere. Okay, now it's correct. It looks correct at least. So you got 2a square upon b square, and then you got, oh, that a is common, so just a, and then 1 minus e squared. Sure. This thing just turns out to be a square. This cancels. It's 2a. Yeah, that's the major x. I forgot to multiply by d. Okay, now it's correct. Next. Why am I deleting this thing? Whatever. Delete. Okay, I didn't even mark down my answer, so anyway, it's a proof question, doesn't really matter. Okay, next you have 12. P and Q are points on the ellipse. If the chord PQ touches the ellipse, this ellipse, prove that secant alpha or secant beta equal to 2, where alpha beta are the eccentric angles of the point P and Q. Chord PQ touches this ellipse. P and Q are points on this ellipse, and chord PQ touches this. It's 4x square upon a square plus y square upon p square minus 4x upon a is equal to 0. That's weird. Oh, so it's centered around x equal to a, I think. No, wait. No, it's not. Mhm. The chord PQ. Okay, touches this ellipse. Prove that secant alpha is these are the eccentric angles, right? You know what we should do? Yeah, just go to the unit circle, right? So what I'm thinking of is just applying a reverse transformation such that we go directly to the unit circle. So not even the auxiliary circle. Shrink that to the unit circle. I mean the geometries are still the same, right? Because I say geometry, but it's supposed to be the shape of the whole thing. So like alpha beta, they don't change. They don't change. You go to the auxiliary circle, alpha beta are the angles, actual angles, not just eccentric angles. And now you shrink, it still doesn't change, right? And this property would still hold in that case. So what we should do is just consider the circle x squared plus y squared equal to 1 and 4x squared plus y squared minus 4x is equal to 0, right? Yeah, that's much easier to deal with. So just add 1 on both sides, supposed to be 2x minus 1 squared plus y squared is equal to uh, that's equal to 1, right? So x minus 1 upon 2 square upon yeah, like 4 over there. So gonna divide by what? Okay, it's already okay, it's like 1/4. So 1 upon 2 square you can say, okay, like plus y square is equal to 1. So first you just got a circle like this and then you have another ellipse, right? Yeah. And you are saying this is a tangent to that. Okay. It's more like saying, okay, so a tangent to this ellipse cuts, cuts this circle into points which have an alpha beta as angles, right? And then you have to prove this thing. Of course. I guess that's better. But no, I would like to go the other way. Hmm. But we do want to deal only with the auxiliary circle. We don't want to do this thing. Hmm. Yeah, fine. Think about it. Think about it. What would be the equation of this chord? If this is like alpha, this is beta angle, right? What's the equation of this chord? It should just be, y minus cosine alpha upon, sorry, sine alpha upon x minus cosine alpha is equal to, maybe this is not the best way actually. And this is like tangent to this particular ellipse. It's centered around so like 1 upon 2, and this has the major axis being 1 upon, sorry, semi major axis being 1 upon 2, right? So this is how the ellipse looks like. Okay, cool. So yeah, and you're seeing a chord to that is a tangent to this ellipse, right? So maybe like this thing, whatever. But that's another way you have to do this, right? Okay, so y minus sine alpha upon x minus cosine alpha is equal to, so it's supposed to be like sine alpha minus, okay, there's supposed to be 2 sine of alpha minus beta minus alpha upon 2. Subtraction, right? So 2 sine of the difference, which is alpha minus beta upon 2. So yeah, and then sine of the sum, alpha plus beta upon 2. So like this will cancel out, but in negative, and it will just be negative cot of alpha plus beta upon 2. Wait, all we care about is like secant alpha plus secant beta. We don't actually care about what this thing is. Oh, huh. Maybe we should not have done that, I guess. Just let it be like that. So the cosine alpha, cosine beta minus shit, sine beta minus sine alpha upon cosine beta minus cosine alpha, just cross multiply, I'll get, this is just too much. It's just too much, right? Yeah. Why secant alpha plus secant beta? What's that got to do with the thing? Secant alpha, I don't know. Certainly must be tangent to that. 1 upon cosine alpha. Hey, come on, think about it. What would be the equation of tangent for this thing? So for this, guys, like y is equal to mx. Instead of x, I'll just put x minus 1 upon 2 plus or minus square root of a square. M square is like 1/4 m square plus b square just 1 right? And now what? Now we got the equation of tangent. I'm thinking that maybe you have cosine theta comma sine theta as a point that fits into this thing, right? And then you need to figure out what values of theta will actually work. Yeah, that's more like it. Just putting that over here. Oh, by the way, just gotta put this thing squared. Yeah. So 1/4 m squared plus 1. And now, yeah, you have to deal with it. I hate this. Isn't there some easier way to do this? I guess there isn't. There really isn't. Secant alpha plus secant. Why is that quantity so important? That's equal to 2. Wait, isn't that like the minimum value of both of them? Yeah, wait. Secant alpha. Oh. Oh well. I mean, I can clearly see why that would happen in the first quadrant, but what about the other quadrant? So, yeah, then it's not so obvious. But you have to keep going. You'll have to see what happens. So, maybe first of all, multiply by 4. Nah, just square it right away. Y minus mx plus m upon 2 square. That should be y square plus m square x square plus m squared upon 4. Maybe this idea will fail. Who knows? Because, yeah, I think it has a high probability of failing. There's not like some other x, y value in there. This is not nice. Nothing works. Nothing works here. Okay, keep on going. Keep on going. You got 2 times of this times that is supposed to be just, mx, sorry, my, minus m squared x. Okay. Plus, so these two multiplied supposed to be minus 2mx. Yeah, that's just horrible. Mxy. I'm not interested in that in that case. Sure, you'll get a solution to this thing and whatever. Will it be worth it? No, it won't be. It fits in the particular format. What if I do like, okay, x squared plus y squared equal to 1, so whenever I will see, okay, like x will just replace that by okay, 1 minus y squared, something like that. But then with these linear terms, you have no way of doing it, right? Yeah. So then what do I do? So you got this thing and okay, it's supposed to be like minus 2mxy. So to 1/4 of m squared plus 1, this cancels. Okay. So y squared plus m squared x squared minus 2mxy plus my minus m squared x is equal to 1. It's like minus 1 equals 0, whatever. That's the equation, right? That both of these must follow, right? So any point that lies on any tangent to this thing, that must follow, right? For the tangent slope is on the m. Wait, shouldn't this have been like... oh wait, I think this is like a pair of straight lines, is it not? Maybe it's just a pair of straight lines. Let's try it out. Yeah, I guess it really is. So, well, that's weird. It's a pair of straight lines. Fine. We know what straight lines we're talking about. Yeah, right. But then this M thing, it's just, how do I deal with that? Or we could adjust this ellipse. Prove the secant alpha secant beta equal to 2 where alpha beta the secant plus. Why is this so difficult? It's, I mean, it looks mundane, but it's so complicated. I did the whole thing, yeah. Graph it out, looked at everything. It's still just that complicated. Is there no other way than, like matching it and seeing what the equation becomes out? Okay. Tangent. Hey, what if, so we don't care about plus minus, right? Okay. So to not get a second degree, we could just, start putting stuff in here and maybe we could get something out of that. That's one way of thinking about it. Or, you can get y and x in terms of m and then have, and then like some kind of equation that, what am I thinking? I think it's gonna work like that. Some kind of equation that you should follow. No, it doesn't work like that. What do I do now? What do I do? The 2 points that lie on this equation. So it's either plus or minus. So 2 points that lie on this equation are given by that. Okay. Okay, cool. And what after that? How do we get to this condition? There's no way of algebraic. I mean, how will we get rid of the sine alpha term? Is there even a way to get rid of that? Secant alpha plus secant beta equal to 2. Wow. Awesome. Oh god. Now I'm just completely out of any methods now. What do I do now? What do I do? Where's all the other stuff? Where's sine alpha? Where's that must also have been there, right? Yeah. What happened to them? Why is that not there? It's like it can't just touch in the first quadrant. That would be not good. This just follow this kind of equation. Wow. It's not helping. It's not helping really. I guess the only way is so the only way is really just to directly square this thing, right? So that you get an equation in x basically, and then from that maybe you can figure out what 1 upon x plus 1 upon 1 upon x1 plus 1 upon x2 should be, and then you will have this thing. I don't want to do this because you got radicals and everything, but if there's no choice left, we have to do it. Just call this thing as, I don't know, c for now. So it will be c, and remember that c square is equal to 1/4 m squared plus 1. Now we'll have to square this. I hate this, yes, but there's no other way. So y square is equal to, what am I doing? And then it's supposed to be m square x square minus, so m square times, it's supposed to be minus x, right? So minus m square times x, and then plus 1/4 m square. That is for the first part. And then you also have to do this other parts like plus c square, and then 2 times of this times that, which is so m times of 2x minus 1 times c, which is cmx, and then minus cm. Sorry, 2 times of that, right? But now we know that, oh wow, this, why is that over here? Okay, that's not squared. That's not squared, right? And then you can write this as 1 minus x squared, right? Because of course, and that just means like 1 is equal to m squared plus 1 times x squared minus m square x plus 1/4. Oh, so that's where this comes. Okay, fine. Just keep on going. Keep on going. We'll get to some nice thing. So minus cm. I don't like this thing. Well, whatever. Hey, isn't that like c minus 1 upon 2m complete square or something? This extra term, I don't like this. This makes everything hard. You need to have 1 upon x1 plus 1 upon x2. It's supposed to be x1 plus x2 upon x1 x2. You will need everything for that. Or you just divide by x squared and everything 1. Maybe. Okay, c squared is supposed to be. This is not working. You're getting this extra term, which I don't want. If it was just like, okay, c squared is equal to 1/4 m squared plus 1. Okay, even that doesn't work because. No, doesn't work. Just doesn't work, huh? Now what do I do if it doesn't work? Oh, and why am I getting 1 upon 4 m square? Is that what you should get. No, you should not get that. It is supposed to be 1/4 times m squared. If it was negative c or something, it would have made sense for us to cancel that out, but it's not like that. Okay, you can't just cancel it out like the usual. No. Even this is not giving me anything. M squared plus 1 and then x squared. So x terms are just over here, minus m squared x. We don't care about them, right? And then you got this minus 1. Okay, so like 1/4, so it's supposed to be m squared. M squared upon 4 plus c squared minus cm minus 1. All of this is equal to 0, right? So to get this, it's just supposed, and by the way, like plus of this, guys, right? Just divide by x, and then it's supposed to be, right, you'll get this thing upon that. That's going to be 1 upon first root and plus 1 upon the other root, negative, of course. So it's going to be m squared upon all of this. M squared upon 4 plus c squared m minus c m minus 1, right? They are expecting this to be 2. Yeah, why? I don't see why that should be 2. There's a linear term of c over here. It will contain a radical. There's no way you can make it 2. I think this is wrong. I mean, if it's not provable, there's only one thing we can do, which is try to disprove this, right? Okay, I'm not gonna work for that. If it's already wrong, I'm gonna skip this. You guys can try disproving this, or if it's correct, give me a nice method of proving this. Right, 13th. A straight line AB touches the ellipse and the circle, focal chord of the ellipse, parallel to AB. So you got some kind of ellipse, and you got another. We have a circle also centered around 0, and R is between A and B. Okay, so like this. Okay, a straight line touches this ellipse and this, right? So it's a common tangent to these. Fine. Focal chord of the ellipse parallel to AB. So AB. Okay, it's like this line parallel to that line. Right, intersects the circle in P and Q. Circle in P and Q, and it's supposed to be passing through the focus. Right, find the length of the perpendicular drawn from the center of the ellipse to PQ. The perpendicular drawn from the center of the ellipse. It's already so not good. So you want to find this focal chord, and then you want the length of perpendicular from this point to that point. Hence show that PQ is equal to 2B. And if you already know that's supposed to be 2B, then I mean that's B right here, and this is supposed to be equal to R, and then it just means like this square root of R squared minus B squared. Interesting. We'll see what we get. Okay, common tangent for these two. So y is equal to mx plus or minus square root of a squared m squared plus b squared, and then this guy just has like y is equal to mx plus or minus square root of r squared m squared plus r squared. Clearly these inside quantities are the same. That just means like m squared, and then you got a minus r squared is equal to r squared minus b squared, which means m squared is just equal to r squared minus b squared upon a squared minus r squared. Okay, awesome. Yeah, and then with the same slope, so the square root of that thing, right? With the same slope, you've got this line, right? And it's passing through the focus, so it's one of the focus. Just say let's say negative AE. So the equation would just be y is equal to 0. Yeah, and then you got m times of x plus AE. Yeah, and you just want like, okay, the distance of 0 comma 0 to this guy, right? What will that be? It's like minus of this guy equal to 0. Fine. So MAE, more like magnitude of m times AE, whatever. And that thing upon square root of 1 plus m squared. Yeah, that should do it. And yeah, you just want, right, you want to figure out what this distance is. So just plug this value in here. Square root of r squared minus b squared upon a squared minus r squared, and you got a e upon square root of, so 1 plus m, so it's like 1 plus all of this. Combine, you just get a square minus b square on the top, right? Cool, this cancels, perfect. Yeah. Okay. And this thing is just like AE, so this cancels as well. So it's supposed to be square root of r squared plus b squared, as we expected, right? I mean, this was just that. So there we go. This distance is supposed to be equal to sort of r squared plus b squared, and that just means like this has to be equal to b, so that we get that thing. Fine. Next question. Show that the area of sector of standard ellipse in the first quadrant between major axis and a line drawn through the focus. What? You got an ellipse, area of sector of standard ellipse in the first quadrant. First quadrant, okay. Area of sector of between the major axis and a line drawn through the focus. Line drawn through the focus? What is this thing? So this is the point to which the line is drawn through the focus. Reading this gives me, what is this? Between the major axis and a line drawn to the focus. Just okay, first of all, you got draw a line to the focus. Now what's theta? Theta is the eccentric angle of the point to which the line is drawn through the focus. So maybe like this point, I guess. And you are talking about the area of sector of the standard ellipse in the first quadrant between the major axis and a line drawn through the focus. What sector is between the major axis and this line? What? So what is this? Maybe you mean like this area. Is that what you mean? That's equal to this guy, half AB times theta minus E sine theta or something. Okay, so this has to be like theta, whatever. Oh, it just makes no sense now. Oh, I mean, of course, this angle is not theta. The eccentric angle is theta for this guy. Is it this area I'm talking about, or are you talking about this area or this whole area? What are you talking about? What do you mean by sector? Sector must mean this thing, right? But then what's it got to do with this line? And you are saying it should be through the focus, right? That's through which you are drawing the line. What do you mean by sector? Standard ellipse, of course. I think it means like this. Okay, just delete everything. You got this focal point, and then this is the thing, right? I guess that's what they're talking about, right? So you want to find what this area is. Is that correct or not? I think that's right. Okay, so then of course it's a linear transformation and everything, so you can just, you know, make it go up. So like make this a circle basically, right? So we'll just have to figure out what this area is first of all, and then once we find this area we can figure out what this is just by making this b upon a times first. This angle is theta. Okay, we know this whole area, yes, that we know. Okay, what else do we know? So you kind of know what this area is, I guess. Yeah, you also know what this area is actually. You also kind of do know what this area is, just that we are not, I mean, that's not easy to find, but you do know what that area is. Think about it, the whole sector minus this triangle. That's better. So this triangle's area, to figure that out, I mean, okay, it's not that hard. This is just AE and this whole thing is just A, and this is theta's like half A square E sine theta. That would be just this area, and then this whole thing would just be, right, it's just like pi r square upon the pi square, and then you got theta upon 2 pi, so theta upon 2r squared basically. So theta upon 2r squared, and then it's just a squared basically, minus this guy. That's going to be this area, right? I guess that's what they want. So 1 upon 2, and then a squared upon 2 actually. So what's the answer? What did they give us? Half AB. Oh yeah, of course, you have to multiply by B upon A as well. So this is actually going to be this thing. So yeah, they do mean this area, but they worded it so improperly. It doesn't feel like they're, I mean, why would they call this a sector? Doesn't look like a sector to me. It should be from here, right? Okay, anyway, next. 15th. A ray emanating from this point is incident to this ellipse at the point P with abscissa 3. Some point is on the ellipse, it's like x squared upon 25. Yeah, okay. Plus y squared upon 9 is equal to 1. So you got this ellipse. It's basically like 16, yeah, that's the thing. 16. That's AE. Ray emanating from a point -4, 0. Isn't that just the other focus, right? At a point P with abscissa 3, so x equal to 3. Fine. Find the equation of, if x is equal to 3, it's like that's 9 upon, figure out what y should be, 9 upon 25. So 1 minus this guy is supposed to be equal to y squared upon 9, right? That's going to be 16 upon 25, I guess. That's equal to y squared upon 9. Is that right? So y upon 3 is equal to 4 upon 5. I mean, it could be plus minus, but whatever. Y equal to 12 upon 5 is where it is. So 3 comma, the abscissa is what? Once again, 3, right? So 3 comma 12 upon 5 is the point P. And then we know the other ray will just go through the other focus, right? 4 comma 0. So there we go. You got the equation with it, right? So y is equal to 12 upon 5 plus the slope, which is, oh god, I hate this. So 12 upon 5 upon, oh, that's 0. That's 0, right? Let's find this thing. Then you got 3 minus 4, it's like -1. So negative 12 upon 5. That's x minus 3. No. Wait, what? Why am I doing this? Okay, whatever. Now it's halfway done. Don't stop. That should do it. Wow. Awesome. Fine. So it just means like y is equal to, it's like 5, y is equal to 12 minus 12x plus 36. So, right, 12x plus 5y is equal to 48. That's the equation. So this is the equation for what? For question number 15. Question number 16. If P is the length of the perpendicular from focus S of this ellipse on any tangent at P, length of perpendicular from the focus S of the ellipse on any tangent at P, okay, show that B square upon P square is equal to 2a upon length of SP. Seriously? Seriously? Can't believe this. And that thing minus 1. Wow. So basically they're saying figure out what P is, right? So what's the perpendicular length basically, right? Fine. So oh god, x cosine theta upon a plus y sine theta upon b equal to 1. That's our tangent. So you're going from AE comma 0 to this thing, so it should just be like e cos, just go like 1 minus e cosine theta, and that thing upon square root of all that stuff, right? So c square upon a square plus s square upon b square. This is what p is. So square root, that's, yeah, like this quantity b square upon b square is just going to be b square upon, sorry, b square times all of this, c square upon a square, and then plus s square upon b square, and that thing upon 1 minus ec squared. Now this thing is s square plus 1 minus e square times c square, which is c square minus e square c square. This cancels, just 1 minus ec, sorry, e square c square, and then upon 1 minus ec square. Isn't that just 1 plus ec upon 1 minus ec? And you are saying this is equal to 2a upon, and this length we know, like length sp, that should just be like a upon e minus ac, and that times of e, right? So this would just be a times of 1 minus ec. This cancels, right? And then that minus 1, which is of course like that cancels, just 1 plus ec, and that upon 1 minus ec. That's it. Okay, right, next 16 done. Let's go to 17. In an ellipse, x square upon a square plus y square upon b square equal to 1, n1 n2 are the lengths of two perpendicular normals terminated at the major axis. Then prove that two perpendicular normals terminated at the major axis. What? Terminated at the major axis. What does that even mean? Oh, okay. So like you got normals and then only till it reaches axis. Then from, so we want length, right? That's why. Then prove that this. Okay. Oh god. Perpendicular, right? That's important, I guess. So the chord of contact is from diameter circle, at some point on diameter circle. Huh? So what is the length caught between the ellipse and the the x-axis of the normal, right? Normal is of like what? I'm starting to hate this, Oh god. What's the normal like really? So you got the point a cosine theta comma b sine theta, and you'll just have plus some multiple of this vector. By the way, for tangent, the vector was like the uh, the vector that's normal to the tangent. Okay, that's what I should say. That would just be cosine theta upon a and sine theta upon b, right? Yeah, so c upon a and s upon b. That should do it, right? So we just want to figure out when will this like reach the x coordinate or something. Yeah. So for that to happen, um, like r upon a plus a should be equal to 0. That is, r should just be negative a square. So there we go, negative a square times c upon a and then s upon b. This is the vector that you're looking for. So the length really is just the magnitude of this guy, which is a square, and then you got square root of, yeah, you get the idea. C square upon a square plus s square upon b square. Maybe you can take that 1a inside. It's supposed to be a times of square root of c square plus, oh no, it's gotta have that b square. That's wrong. Maybe take a b square inside, So a square b upon b, and then take this b inside. It's going to be square root of, so 1 minus e square c square. That should do it. So that would be the length. Let's just say n1. Right, so that's for alpha, and then n2 would be a square upon b, and then you got right. And what you want is the reciprocal. Okay, that's different than what I expected this to be. Right, and that's equal to a square plus b square upon b power 4, you say. Interesting. We'll see what we get. B upon a square, that thing squared first of all, actually. So b squared upon e power 4, and then you got 1 upon 1 minus e square c square alpha plus 1 upon 1 minus e square c square beta. Right. Now we should figure out like when these two will be normals, right? So this is the vector that we're talking about. These would be perpendicular if these are perpendicular tangents, so perpendicular normals, right? So you just have cosine alpha upon a and then cosine beta upon b plus sine, upon a, and then sine alpha upon, what am I doing? Upon b, and then sine beta upon b is equal to 0, right? That means that goes over here is like b square upon a square is equal to negative tan alpha tan beta. That should do it. which is like obvious. Okay? Like tan alpha tan beta is equal to negative b square upon a square as expected, because yeah, I mean, just going back, so deforming, you would get this little thing, right? Yeah, sure. So there we go. That's nice, I guess. And now what do we do? I don't know. Other than multiplying this out, do we have any other choice? I don't think we do. So if this happens, what can we say about cosine square alpha? Yeah, that's another complicated thing to do. It's gonna take forever like this. Maybe we should first of all convert this to secant square alpha, because that can be written in terms of tan, right? Maybe. Let's see what that does. So we this gives like 1 plus t alpha square upon secant square, like 1 plus t alpha square minus e square. So basically 1 minus e square plus t alpha square, right? And then the same thing over here. Okay, and then you will have to cross multiply this out. So b square upon a power 4. Okay, just omit this for now. You'll have to see what this turns out to be, right? So this times that, it's going to be 1 minus e square plus t alpha square, and then so t beta square times all of this, right? So plus t beta square plus t alpha square times t beta square. But that thing is just, like 1. No, wait, that's equal to what? B square. Oh, that's equal to 1 minus e squared, in fact, right? Actually, that thing squared. So plus 1 minus e squared squared. And now the same thing over here as well, except that you have like a slight difference of, just changed. So t beta square, and then you got t alpha square plus 1 minus e square square. Okay, and all of that upon, so 1 minus e square square, right? Plus 1 minus e square, and then you got tan alpha square plus tan beta square. Okay, I guess it's going good till now. And then once again, you got another 1 minus e square square, like 2 times of this guy, right? Over here as well, just got 2 times of that. But now these combined, it's different. Right, where did that go? Oh, there's the other. No, okay, that we used up. Nothing wrong with that. Okay. Oof, just going like that. Got this extra stuff. Got this, right? So this is, let's just call 1 of e square as, I don't know, m for now. It's gonna be 2m plus tan square alpha plus tan square beta. Oh, I actually 2 times of that, huh? So yeah, okay, 2m plus 2 tan square alpha plus 2 tan square beta plus 2m squared, of course. And that thing upon 2m square plus m times of tan square alpha plus tan square beta. You can just take a m out, I guess. So this would be basically m times 2m plus tan square alpha plus, hey, isn't that like tan alpha plus tan beta square? Because like they multiply to, oh, they multiply to oh shit. Wait, what? Okay, the good thing is we only cared about tan like square of those, right? So this is still okay. Okay, no big deal. This is awesome. I mean, it just keeps on going. Like, what is this? We will never get to the solution like that. Something must have gone wrong. Okay. Once again. So, tan alpha tan beta is just equal to, right, negative m. And then this must be the case. It's like 1 plus, call this thing AB for now. So AB is equal to negative m. And what we really want is 1 plus a square upon m plus a square plus 1 plus b square upon m plus b square, right? That's what we're looking for. Yeah, right. So let's see what we get. M plus ma square plus, plus b square, and then plus a square b square. So a square b square would just be m square. And you want to sum this up. So it's going to be 2m square plus 2m plus m times of a square plus b square. It's not m plus 1. Oh, that's the term that we're missing, right? Okay, so now it's going to be, yeah, over here, okay, it's going to be 2 plus a square plus b square. Sorry, 2m times all that stuff, right? Yeah. So 2m plus a square plus b square, and all of that times m plus 1. Cool. And then upon, so multiplication of these guys supposed to be m squared plus m times of a square plus b square plus a square times b square, which is actually just m squared. So there we go. Just take that m out, and then it's exactly that. So it's supposed to be m plus 1 upon m, and then that times this thing, right? Yeah, b square upon a power 4. So this whole thing, oh, and by the way, m times of a square would just be equal to b square. So like b square upon m, that's just a square, right? Yeah. And then you can make this come inside. Supposed to be b square plus a square upon a power 4. Finally, it's done. So there we go. This is the thing. Yeah. Okay, next. Okay, so let's go to 18th now. If the tangent at any point on this ellipse makes an angle alpha with the major axis and an angle beta with the focal radius of the point of contact. What? Sorry, repeat that. Tangent to this ellipse makes angle alpha with the major axis. So, okay, fine. Alpha with the major axis, fine, whatever. Okay, that's not what I should do. Okay, this is alpha. And angle beta with the focal radius of the point of contact. So, right, this would be beta, I guess. Yeah, right. Wait, this should be beta, whatever. Show that the eccentricity E of the ellipse is given by this. Okay, cosine beta upon cosine alpha. You know what? I seriously think that at this point you should use the other parameterization, right? So other parameterization goes like this. Okay, you got this ellipse or any conic, in fact. Right. So the tangent to this thing, right? That makes angle alpha with the x-axis, and beta is beta is this angle. Sorry. Right. And we need to figure out eccentricity, of course. So you know how it goes. Like, thing is, it's a e power I theta upon 1 minus e cosine theta. That is the parameterized form of this point where this is the origin, right? So to get the tangent, you just need to figure out so d upon d theta of this thing along what vector is that, right? Once you figure that out, this will be doable, right? Wait a second. Yeah, okay, reflective property doesn't work like that. Sorry. Yeah, it doesn't work like that, of course. Okay, now let's do this thing. Yeah, it must be like this. What else? What else could be the thing? Okay, let's differentiate that. It's gonna be e power I theta, and then you got upon 1 minus e cosine theta, whatever. But that times of iota, because and then omega is there, but we'll get rid of that. Don't worry about this thing. And then plus, so wanna take the derivative of that guy, right? So negative is not positive, but then once again negative. So supposed to be negative 1 minus e cosine theta squared. You got that sine theta right there. And this is supposed to be e. Oh, and also like that e. And then e power I theta. So this will pretty much just be e power I theta common. And then you got just 1 minus e cosine theta squared multiplied by that. You want to reduce this anyway, right? Okay, so it's gonna be iota times this guy, and then minus e sine theta, so minus e sine theta, and then plus 1 minus e cosine theta times iota, right? That should be the thing. So yeah, and well, I'm saying it's theta and all, but right, the thing is, like, this angle is just alpha plus beta, so theta is alpha plus beta, fine. And this angle, like, okay, the tan inverse of whatever tan value you will get, that is the angle by which you have rotated, right? So yeah, this was making this angle, but now you rotate it by that thing. So that's going to be beta, right? So beta, or I just say tan beta instead. So tan beta is equal to minus e cosine theta upon, yeah, negative, but it doesn't matter. Just look for the magnitude. Okay, and we know that theta must just be alpha plus beta, right? And now let's see what this gives us. Sure, it's like e sine theta tan. Okay, maybe we should not. Yeah, we should just right away put it as alpha plus beta, right? Because we want to get between terms of alpha and beta only. Wait, but this whole thing would be interesting. Very interesting. Come on, think about it. Yeah, whatever, just keep on going. Right, so theta is equal to alpha plus beta, just put that in there. Let's see what this turns out to be. 1 minus e cosine alpha cosine beta, and then you got plus e sine alpha sine beta upon e sine alpha cosine beta plus e sine beta cosine alpha. And then let's just divide by cosine alpha cosine beta and see what we get. So it's like secant alpha secant beta minus e plus e tan alpha tan beta upon e tan alpha. It's like e times the tan alpha plus tan beta, right? Yeah, and all of that is equal to tan beta. Just multiply. Let's see what we get. Secant alpha secant beta minus e plus e tan alpha tan beta, that's equal to e tan alpha tan beta plus e tan square of beta. Okay, this cancels out, and then that comes over here. It's supposed to be e times of secant square beta, and yeah, now it's perfect. This cancels out. So really, like, e is equal to cosine beta, because that goes over there, cosine beta upon cosine alpha, and that's exactly what we want to do. Done. Nice. Next question. Using the fact that product of perpendiculars from either foci of the ellipse, oh, suppose just erase this because, yeah, whatever. Using the fact that the product of perpendiculars from either foci of an ellipse upon the tangent is b squared, it used that the following row back. An ellipse with a and b as the length of its semi-axis slides between two given straight lines at right angles to one another. Oh, that's important. You know what? Maybe you should do a more general thing. Not right angles, we'll say it's any random angle. Right? So you got any random angle, call this thing alpha or whatever. And so ellipse slides between these. So that its locus of its center and the locus of the foci of this curve, right? Okay, cool. So yeah, it slides like that. So it's wait, the length of its semi-axis. Okay, these are fixed, right? Oh, so the dimensions of this ellipse are like fixed. Okay, understandable. Fine. Wait, oh, we know this particular case. It's like this will sit on the director circle of ellipse, so its distance from the center is always constant. But no, okay, we want to do it for, you know, a more general something. Yeah. Ellipse. Okay, think. The foci might be anywhere. We don't know what's happening to them actually. Yeah, right. If that's a tangent to the ellipse, then like what property is it that ties everything together? Reflective property, maybe. Doesn't look like that. You know, something else maybe. If you assume the focus to be somewhere over here, I don't know. Anyway, A and B are constant, right? That's important. I think that's supposed to be important, at least, right? Like length from here and length from here. And then something like that. Okay. So some of these two lengths, like wherever the point of contact is, we don't know. Some of these two lengths is actually same. Wait a second. If the focus is over here and like this is S1, S2, I don't know, just randomly doing this, okay? We don't know where the point of contact is going to be, right? But we do know that this is a tangent. So if I reflect it like that, you will actually get the point of contact. So there we go. That's supposed to be point of contact. And similarly, if you just reflect it, you're gonna get the other point of contact. And there we go. That's the other point of contact. And you also get S2. So just using this thing, right? So the thing is like reflect and get S2. Understandable. Okay, cool. And then what? What after this thing? Once you got S1 and S2, I mean, it's much more doable now. Yeah, sure. But it's still quite complicated actually. You have to do a lot of algebra to get this done. So the center would be somewhere over here. Yeah, I mean, we just want where the center is and something like that, right? Yeah, nothing else, of course. That's a tangent to that. Sure. And these two lengths, they must be 2A, in fact, right? Yeah. Okay. Okay, awesome. And then what? Like, okay, you know how to do this. Like, okay, you got this thing, and oh yeah, okay. So we actually don't know in what direction we have to go. That's the problem because S2 is still unknown. So only thing we know is from here you wanna walk 2A steps. Oh yeah, so it's gonna right. The way to do this is just first of all reflect and then construct two circles and then point of intersection will be what you look for. Crazy, huh? Yeah, very crazy actually. So these two circles, I mean, of course, they got these as the centers. This distance is not even necessarily 2A, right? I mean, okay, most likely it is not 2A, just not. Okay. What if I like go the same length, but okay, we don't know what the point of contact. Yeah, calm down. We don't know what the point of contact is. I can see how it being perpendicular really helps, but in the end, we must be able to do this general case because then we can extend it to other questions as well. There must be something. There must be something. That's perpendicular and everything. I understand that. It's just like this line is 2A. How do I make use of that? Like draw these circles out and then make the equations actually. That's just too much, isn't it? Yeah, right. How do you get the center right away? No, you can't. You can't get the center. You have to first of all figure out what S2 is, right? Let's say S1 is like represented by Z1. Okay. This is the real axis. This is some vector called this thing as, and by the way, by vector it's meaning a complex number, right? So this might just be, call this A vector or A hat. A hat is better. So just a unit vector basically. And we want this thing, right? So for that, what we'll do is we'll just do Z1 upon A. That just gives us, the rotated vector, right? So with respect to this guy, whatever this vector is, yeah, you want to make that like reflect about that. So you're just gonna take the conjugate of this guy, right? Yeah, of this whole guy. That's gonna give us this vector, but still rotated, and this times A. That is actually what will give us, this thing as seen by this guy, right? Same stuff to get this point as well. Now, once you have that, it becomes a lot more complicated because now you actually have to figure out what this point is. That's definitely much worse. Yeah, right. Something else, some kind of transformation. No, the only way to get something doable is like just shear this. But then when you shear this, your length will change most likely, right? And that makes everything complicated. I don't want the length to change. I want this to be 2A. We don't know in what direction this should be going. Oh, and by the way, I used A to some kind of vector. I don't know, n. N is a unit vector. So this thing is going to be like n squared, and that types of z1 hat. Sorry, z1 conjugate, right? And similarly, you're gonna do for this. But for this guy, just take the reflection is like, okay, that's easy because it's going to be z1 conjugate. So now you got these 2 points, and yeah, we just need to figure out what this point is. Hey, wait, these two lengths are the same, right? So these must lie, like this point must lie on the perpendicular bisector of these two lengths. Sure. Yeah, that's understandable. Okay, you can of course figure out what this midpoint is and what this length is, and then rotate this vector by 90 degree. And yeah, but this being 2A, how do you use that fact? Right? We don't know till what distance you have to go. Okay, I think that's a way to figure out the focus, but not the way to figure out the locus. That rhymed almost. Yeah, because it's just too complicated. So fine, let's do the question as it is. That is with perpendicular axis. Okay. So let's read the question once again. Right. Ellipse with A and B, first length, slide between the two, one straight line. Right, we just know its center is gonna lie on that. Okay, yeah. Locus of its center is a center. So locus of its center is a circle. We just showed it. And the locus of its foci is this curve. So yeah, like okay, that and that. Hmm. If the foci is somewhere, you can always figure out what the where the center is supposed to be, something like that, right? No, it's not that easy. Locus of its foci is this curve, Okay, x squared plus y squared. So with the radius times x squared y squared plus e power 4. That's weird. Yeah. So we have to use the fact that the product of perpendiculars is supposed to be b squared. Let's try to do it. So yeah, the center might be somewhere over here. We know what r is supposed to be the square root of a squared plus b squared, right? If this angle is like theta, you got the center somewhere over there. We don't know where the foci actually are. It might be like this thing, or I don't know. Okay, and then the thing is, like these perpendiculars, they must add, they must multiply to b square, and similarly these perpendiculars must multiply to b square, right? Yeah, that's the important bit. Okay, so whatever point you get, for this thing r for now, so like r e power I theta, and let's just say this whole thing is so this new angle is like alpha. Okay, so plus, and we know it's supposed to be ae, so ae e power I alpha, right? That's this point. And also you can do minus ae e power I alpha, right? And then r e power I theta. So you want the product of these product of the, let's just say real part, and then imaginary part, imaginary part, both must be b squared. That's important, right? Okay, so what does that mean? The product would just be like, oh, and by the way, it's like negative, that cancels out. Cool. It's gonna be r squared cosine squared of theta. So product of the x coordinates. That's what I'm talking about. And then minus a square e square cosine square alpha. That has to be equal to b square. And similarly, yeah, like for sine square alpha as well. So r square sine square alpha theta minus a square e square sine square alpha is equal to b square, right? That also has to hold. I mean, okay, the addition of these would hold in any case, right? Because r square plus a squared e squared, that's just like a squared plus b squared minus a squared e squared, which is actually just Wait, is that right? Product is supposed to be squared. Yeah, okay. A squared plus b squared minus a squared e squared. That's only b squared plus b squared. Wait, isn't that like 2b squared? Oh yeah, it is 2b squared. You add this, is supposed to be 2b squared right there. So that works out. I mean, if one of them works, the other must also work because you can just subtract that equation, right? And get this thing. Okay, so just caring about this is enough. Yeah. So now what? A square times c square, so c square theta and then minus c square alpha. Okay, that's not the way to do it. For both the foci, this must happen. And the x coordinate is that, isn't it? Okay. Yeah, this is not helping. You want to show that this equation is what we should get. So it involves x square, y square everywhere, right? Okay. Think about it. So for this guy, just have x square is equal to r squared cosine square theta plus 2rae cosine theta cosine alpha, right? And then you got plus, or this might not even work. Still, just keep going. A square e square sine square alpha. Sorry, oops, cosine square alpha, right? And then just have y squared being everything but in sine square. 2rae sine theta sine alpha whatever plus a square e square cosine, so sine square alpha, right? We can of course add these up, right? It's gonna be r squared plus a square e square. That's not really useful, huh? When you can definitely write as 2a square over there or something. Okay, how do I get this thing? R square c square and stuff like that. I wanna get this thing. All you know is just one of these distances. Oh god. And follows this equation. How do we know that? So you're saying x squared plus y squared, it's like multiply that out or something. Oh, why is there this x squared y squared? Maybe divide by that same. Okay. So 1 plus b power 4 x squared y squared. You can't even just do a linear transformation and say that, yeah, that's how it's gonna work. No. Now this is, oh yeah, you have to do it like that. Now what? What do we do? I mean, we can just try forming this left hand side and see if that is equal to this thing, right? So times y squared. That just, yeah, I don't want to do that. Definitely don't want to do that. What can we do though? Let's see how that's gonna help. X squared y squared. No, no. It's got times y. Not really useful, is it? No, it's not. Come on, think. How do we get this? How do we get this? Other than lot of algebra, right? How do we actually get this? I'm starting to think that maybe figuring out theta and alpha, right? In that way you could, okay, no. Most likely it's not going to work. So it does, like alpha theta do follow this equation at least. So everywhere that we got this thing, we can just write this as a square e square cosine square alpha plus beta square. Yeah, okay, we can do that everywhere. So then you can say x square, and then same kind of equation holds with sine square as well, right? So x square is just equal to 2rae cosine theta cosine alpha, and then plus right, and plus b square plus 2a square e square cosine square alpha, right? Okay. So maybe like x square minus b square would work. That would just be equal to 2RAE cosine theta cosine alpha plus 2a square e square cosine square alpha, right? How do we get this thing? Cosine alpha cosine, so theta cosine alpha, right? There's no way for us to get that. Yeah, I mean, just doing the thing doesn't work. But I mean, like, it just has x square, y square, and all that. Not helping. Same kind of stuff goes with y square as well. Now what? So it's like 2a. So yeah, 2AE. Maybe I should have gone the other way and simplified this. Okay, maybe that would have been better. It's still the same thing. Not much has changed. So it's gonna be 2r squared c theta squared and then plus 2RAE c theta c alpha, which you can write as 2r c theta, and then you got r c theta plus so 2r theta is gone. It's just AE cosine alpha, right? Hey, wait, what is this guy? Isn't that just x? Wait, isn't that just x? Because wait a second. R squared. Oh yeah, wait, that is the. Wow, okay, that is equal to like 2xRc theta, huh? Interesting. Then you can do the same kind of thing for y as well. And then wait, you just get something involving only, and for that you just have sine theta, right? Yeah, so you just got y squared as b squared. Same whole, everything is just same. Except that instead of c theta, you just have s theta. And yeah, that's gonna be equal to 2y r sine theta. Just square and add. I mean, of course, after dividing by x and y. So this will be like x minus b squared upon x squared plus y minus b squared upon y squared. That's equal to 4r squared c. Maybe that's doable after all. Okay. This will be like x squared plus y squared plus b power 4 upon x squared plus b power 4 upon y squared, and then minus 2b squared minus 2b squared, it's just minus 4b squared. That's equal to 4a squared plus 4b squared, right? Sure, that goes 1 here, becomes 8b squared. Okay, awesome, I guess. Why does it look like plus or something? No, it's not. Ah, come on. Oh, okay. So this is supposed to be actually this quantity minus. It's supposed to be plus. Yeah, it's supposed to be plus. Not over here. Over here, right? Yeah. Okay. Then it would be plus 4b. This cancels. That's what I thought. So there we go. That should be the equation. What about this guy? Is that the same thing? So okay, let's just simplify this. X plus y squared times 1 plus b power 4 upon x squared y squared is equal to 4a squared. That's the thing, right? So when you divide by x squared y squared, you just get this guy. Oh yeah, so it's correct. Okay, 19th done. So 19th is done as well. So to 20 now. If the tangents are drawn to this ellipse intersecting on the x-axis, constant length c. Something on x-axis, constant length c. Point of intersection, of course, so it will be like this, right? Okay, this thing, this length is a constant c. Okay, prove that the locus of the point of intersection of the tangents is this curve. So first idea, I'm thinking of reversing the transformation. So actually just going to, I don't know, some kind of, let's just say unit circle or something, right? Then just x squared plus y squared equal to 1. Oh, and I'm here like using x square y square, but technically you have to replace x by x upon a after you you have found out the locus, because you want to go back, right? Yeah. And then this length will just, after the transformation, just becomes so the x values just get changed. You just decrease every x value by a, right? Yeah. Yes, like x upon a is now the new x value. So this guy will just have like c upon a as the value, right? So now this length will just be c upon a. So you got this this circle, you got this length c upon a as the constant length, right? And you want to talk about this point. So yeah, where's that intersection point going to be? It's like not that bad actually, is it? Nah, I guess it's doable. Right. Anything like special about this? No, no. Doesn't look like that. Hey, wait, okay, this thing is supposed to be R all of the time, right? Yeah. What about this length? So this length times R, and then that would just be like the area of this triangle, two times of that. And then this R times this length. That's going to be two times of this area as well. The sum of that would just be like R times of this length plus that length. Okay, that's not important. We want a square of those lengths. No, okay, no, it's not even 90 degrees, so you can't do that. Okay, it didn't work out. We want this to be a constant area over there. Then, how do you get that to be a constant area? I don't know. Clearly, it's passing through the center. Maybe that's somehow important. It doesn't look like it's gonna be important actually. That's a constant area. Paragraph curl, does this go through, or yeah, that's what we wanna find. I just have to do this thing. Right, so let's just say, okay, this point, so okay, don't think about it in terms of points or something. Maybe we should think about it as vectors. So if this angle is alpha, this whole angle is beta, this vector going from there is like as e power I alpha, and then this vector would just be e power I beta. Okay, you can rotate by 90 degrees, so I e power I alpha would be this vector, and then rotate by 90 degrees, so you get this vector I e power I beta, right? What we really want is when do these intersect, like this point e power I alpha plus some multiple of this vector, so let's say m times this guy, and then e power I beta plus some other multiple, right? That these two must be the same. That's the thing, right? So whenever these are the same, right, that's the intersection point that we're looking for. And of course, the sum of these two lengths has to be constant. So that's alpha right here. But yeah, okay, that's gonna be pi minus beta, right? So you just want like 1 secant alpha, and then like that's only secant beta, right? Yeah. No, okay, negative secant beta. So addition of that's like secant alpha minus secant beta, right? Okay. So sec alpha minus sec beta. This thing has to be some kind of constant. In this case, we know it's just going to be, where did it go? C upon A. Yeah. And this point is given by this guy. Sure. Wow. And yeah, of course, this is just, so both of these are equal, and both of these are actually equal to x plus I y. Okay. So x is equal to, we just don't want this m and n, do we? No, we don't. We want to get rid of this m and n somehow. Secant alpha minus secant beta, you said. Interesting. How do we get rid of this m and n? I don't know. X is the real part of this guy. That's equal to cosine of alpha plus m sine of alpha. Because, okay, that, oh, minus m sine alpha. Doesn't really matter because I think it does matter. And then it's also equal to just cosine beta minus n sine beta, right? Now I want to get rid of this thing somehow. Yeah. Hey, there's one way of doing this. Just divide by e power I alpha and then think out only the real part. Of course, because 1 plus m iota would just be equal to, so when you divide by e power I alpha, like you are basically doing this thing. Cosine alpha plus I sine of alpha, oops, divide, so it's supposed to be negative. And then x plus I y, right? And in that case, you can actually get the, yeah, like figure out the real part, right? So 1 is equal to, so here, x cosine alpha. Then that's imaginary, we don't want that. I sine alpha, negative alpha times this guy is supposed to be plus y sine alpha. That's equal to 1, right? That's important. Oh, well, that's just a tangent. Why did I not think of that first? Fine. Why did I even think of it like this thing? Okay, we just want this somehow. It's complicated. You can do the same thing for beta as well. So like you want x cosine alpha plus y sine alpha is equal to 1, and then x cosine beta plus y sine beta equal to 1. And yeah, now we just need to figure out like what value of x and y satisfy this thing. That's yet another complicated thing to do. So x times of cosine alpha sine beta minus cosine beta sine alpha. That's going to be equal to sine beta minus sine alpha. Yeah. Not helpful. Oh, and look at this equation. It's even bigger. I mean, that's because it has that a and b and everything. But still, it's pretty big, isn't it? Think. So fine, you'll get x and y and whatever. You have to put them in here, you know. Sure. Secant of minus secant beta. How do I get that? Similar you can do for y as well. But in the end, what we want is not x and y. We actually want alpha and beta, really. So instead of doing all of this, we just want alpha and beta. So more specifically, secant alpha minus secant beta, right? How do we get that? How do you get that? I guess you could just, you know, like say y sine alpha is equal to 1 minus of x cosine alpha, something like that, and then try to square this, and from that you will get something like an equation in cosine alpha, and then that will have some kind of a root. So put one of those roots in here, and then similarly for secant beta as well, right? That's awful. Okay, first of all, just divide by this, so you will just have, and let's say secant alpha is lambda, right? It's equal to lambda x plus y, and then tan alpha is equal to lambda. We don't want tan alpha. It's going to be like y square tan square is just 1 plus lambda square is equal to lambda minus x square, which is just lambda square minus 2 lambda x plus x square. So we just want an equation in lambda square. Lambda square times this y square or something. Minus 2 lambda squared, then minus y squared, I guess. Oh, that already is there. Just need minus y squared. That's equal to 0, right? And we know that the difference of these two roots, right, of this equation in lambda, that's going to be equal to c upon a. So you can figure that out by, you know, taking first of all the sum of the roots, which is 2 lambda upon 2x. It's an equation in lambda, not x. So 2x upon minus y squared, that thing squared, minus 4ac, sorry, minus 4 alpha beta, whatever. So minus 4 times of this thing, okay, like, okay, so plus 4 y squared upon minus y squared. That should be doing it, right? Yeah, and actually that's going to be equal to c squared upon a squared. That should do it. Right. So it's supposed to be 4x squared plus 4y squared times 1 minus y squared is equal to c squared upon a squared. Oh yeah. Okay, there's that 4 over there. Okay. C squared times b squared. Oh, interesting. And now you just gotta replace x by x upon a and y by y upon b. Okay, this it just involves. Oh god, this is different. Fine. Let's see what we get. 4x squared plus 4y squared minus 4y power 4 is equal to c squared upon a squared. Okay, interesting. In there it's supposed to be like this guy squared, right? Yeah. But why is there this y squared minus b squared? Oh, yeah, you had to multiply by that guy squared. It's supposed to be 1 minus y squared squared over there. Ah, of course. That's why it's there. It's got 1 minus y squared squared. And now replace y by y upon b and x by x upon a. So 4 times of x squared upon a squared plus y squared upon b squared minus, yeah, okay, y power 4 upon b power 4 is equal to c squared upon a squared and then times of 1 minus y squared upon b squared. Now time to simplify this. Maybe multiply by a squared b squared first. It's supposed to be 4 times of b squared x squared plus a squared y squared. And wait, why is that over here? Uh, yeah, it's supposed to be y power 4 actually. Wait, did I do that correctly or not? God, y squared. It must have been correct. It must have been right. C upon a. Okay, interesting. So where did that thing go? Why do we have a minus a square b square and not like, where did this y power 4 term go? Oh, so you got this times y squared. Wait, what? Wait, why? No, no, it's not supposed to be there. Why is that the case? I mean, here you have x, but why is this extra y square there? What's going on over here? That guy square short, and then you got shit minus over there. Okay, but still, how big a difference it could probably make? Not so big, right? Yeah, doesn't really change anything because it's still just that much. This thing. Now what? What can I say? Their answer is wrong because my answer is different than theirs. Fine, most likely I made some kind of mistake. Just really tired right now. Okay then, see you guys in the next video. Bye.